So welcome to my talk on systems programming in ATS. So before I start with like ATS syntax or how things work or anything like that, here's the elevator pitch for ATS. It's an ML, but it's not a standard ML, but it's got algebraic data types and pattern matching and all that good stuff. Functional programming is fully supported because tail calls are actually optimized in ATS, and it actually also supports mutual recursion. But the thing that I think that ATS really brings to the table that sets it apart from all the other languages is exactly the same performance and memory predictability of C. Notice I didn't say that it runs as fast as C or uses as little memory as C. I'm making a stronger statement than that. I'm saying you have the exact same control as C. All of that stuff that you do in C, pointer arithmetic, allocating, deallocating, freeing, stack allocation, all of that stuff, that comes back, but there's this whiz-bang type system that makes all that safe. So if you use the type system right, you'll never walk off the end of an array, you will never double free something, you will never have dangling stack pointers, and you will always free all your resources. And I think that's a really powerful thing to have. It just decompiles to C, and except for tail calls, there's no real optimization, and GCC or your favorite C compiler does the rest. Which is why, for the longest time, it was always on top of the language benchmarks. It was always in the top 4 or 5. It was always like C, C++, Ada, ATS, Fortran, and now Rust, right? But for some reason, it was taken down in 2015. It kind of pisses me off. I have no Actually, I now know why it was taken down because somebody in the audience just told me, but I didn't know why until just now. But a couple of big things that like ATS brings to the table are like linear logic to manage resources. So what is linear logic? So if you create a resource, you allocate memory, you open a file handle, you open a database handle, that's a resource. So when you create that, at the type level, you get this thing called a proof object. A proof object is a type level proof that this resource actually exists. And when you want to use the resource, like you want to read from a file or something like that, you have to pass that proof object manually into the function that's reading from the file. And that's how the type system knows that this resource is still viable. So for example, here I have a function called bar, and in the let block, I have this function called open file that takes some file path and returns fd, which is a file descriptor, and some extra syntax, which you've probably never seen before, and get used to that. There's this pipe, and to the left of this pipe is this thing called awesome proof. Awesome proof only exists at the type level. So when I'm trying to read from that file, I have to pass that awesome proof back into the read file so that the type system knows that the file descriptor is still open. And when I close the file, I pass this proof in, that proof gets consumed and is no longer available anywhere. So that means that even though file descriptor may be in scope, if that proof has been consumed, there's no way for another function to read off of a bad file handle or a bad memory address or anything like that. And ATS really doubles down on this for memory. So there's like specialized syntax that says there's a pointer at this address of this size of this type that may or may not be initialized. That's like 5 characters or something like that. And this is how type check pointer arithmetic works in ATS. This is how you can never read off the end of an array because you don't have a proof for it. The other big thing that ATS brings to the table is this idea of refinement types. So refinement types are a way of constraining a large type. So here's this function foo, it takes an int. Int is a huge type. It can go anywhere from 0 to like whatever the max value of int is on your system. So you want to constrain that sometimes. So you modify that with this sort, it's called a sort in ATS, such that sort is an int where n is greater than 0 and n is less than 10. So what this means is that you can never call foo with an integer that's not between 0 and 10. The type checker makes you do that. So between this and linear logic, you can do a lot of like the C-style stuff safely in ATS that you couldn't do in other programming languages. Okay, I've just sold you the Holy Grail, okay? Unfortunately, ATS is the most difficult language I've ever learned in my entire life. I'm not going to gaslight you. The examples that I'm going to show you are hard, and that's why it's called a not-so-gentle introduction, because I'm just passing the buck and saying, I don't know how to make this simple. And some of this is essential complexity, right? Because it's combining, none of these things are trivial. Refinement types, not trivial. Linear logic, not trivial. Proofs, not trivial. C, definitely not trivial, right? And it's a research language. By definition, it's funded in part by the NSF. There's one PI in Boston University, like doing 99% of the commits, right? So when you put all these things together, the first thing that goes out the window is programmer ergonomics, right? So ATS is a tough language to work with. It's really hard. There's no easy story. There's no newcomer onboarding, right? There's no royal road. There's barely a royal cliff. Like, okay? There's a tiny community. If they were all gathered in a bar, I could buy them around, you know? And because of that, the documentation is really sparse. But I present it anyway because I think it has some amazing ideas that I'm not seeing anywhere else. And I think that we should be taking these ideas and running with them. Either cannibalize ATS, or better yet, gather some resources and make ATS itself commercially viable, like clean up some of the syntax, all of this stuff, right? Cool. So the answer to your question, is ATS ready for production? To quote the great Travis Brown, it's ready for production if production is ready for it, you know? So the easiest way to get started with ATS is, I think, with the C interop. So here's a generic swap function in C that swaps two void pointers. Yes, I realize sending size t as an argument is bad. Don't at me on that one. Because the point is that all I have to do to include that into an ATS file is stick it inside of these percentage curly delimiters. And basically, when the C code generator gets to that point, it just takes whatever's inside of those delimiters and jams it into the output file right there. It's exactly that simple, right? And here's a foreign function call to that swap function. It takes two pointers and a size t. And the thing to notice here is that all of the base types in ATS are exactly the same as C. Pointers are pointers, size t's are size t's, ints are ints, longs are longs. There is no marshalling and unmarshalling overhead. We're also going to need malloc, and that's a size t that returns a pointer, right? And here we run it, okay? So I'm allocating a couple of chunks of memory, and I'm swapping it. Cool. Here I'm allocating an integer. All good. Lovely. Here I'm allocating a double. Ooh, that's not good. And here I'm calling swap and telling it that both things are double. That's super not good. And I'm not even cleaning up, right? Okay. So ATS can totally mimic C, bugs and all. You can port your C code to the highest fidelity to ATS by you can port it line by line if you want to. The type system goes to 11, it goes all the way down to C, okay? So the upside is this facilitates gradual migration in a way that's actually, I think, easier to do than something like Rust. You know, you can port the entire Linux kernel over to ATS if you wanted to. But we can do better than that. So here's the old swap function. Let's remove the arguments and give ourselves some space, because ATS needs space, lots of space. So swap is parameterized on some type of type t at ype. That is not a typo. That means a type of unspecified size, because ATS is obsessed with the size of the things that you pass in. So you're passing in a generic type. It's like, okay, you have to tell me whether it's a size something or you don't know what the size is. And that's the keyword for I have no clue what the size of that thing is, because it's a generic argument. Okay, so I'm passing in an address where the address has to be greater than null, another address where the address has to be greater than null, And now the actual arguments, right? I have an I, which is a pointer to a non-null address. I have a j, which is a pointer to a non-null address. I have the s, which is a size argument that takes this type, size of underscore t, that is parameterized on the t at ype type that I just passed in order to be type safe about what kinds of types that I'm generating. So I can't just like pass in 5 as a size argument to like the swap function. And then we see that familiar pipe again. So remember in the example where I was reading from a file descriptor, I was using that pipe to destructure a proof. So when open file returned a file descriptor, it also returned a proof. I can also use the similar syntax to pass in proofs. So here is special syntax that says that there's something of type A at address L1. I'm passing in that proof. And something of type A at address L2, also passing in that proof. The return type is void, but it also returns 2 proofs that there's an A at L1 and an A at L2. Why does it do that? Because ATS by default will consume proofs. Unless you tell it not to, those proofs are gone and not available for use anymore. So if you actually want to use those proofs, you have to return them. By the way, there's special syntax for everything, but there's like special syntax for saying don't touch these proofs, they're fine, don't worry about it. But to be explicit, that's how ATS works. So here's malloc, make ourselves some space, pass in that unsized type parameter, pass in that size argument, which is parameterized on size of A, on size of T, and pass back a pointer to some location L such that there's something of type A at L that is possibly uninitialized. That's what that question mark means. Oh, it gets better. And an address that's greater than null. Okay, cool. So now we have our main function. We're allocating an integer. We're getting back a pointer to that integer I, and a proof that I exists. Allocating an integer, getting a pointer to that, and a proof that that exists, that's j. And now I want to set that pointer to something. I want to set I to 1. So I set I to 1, but I also have to pass in a proof that I exist. It consumes that proof. It's a void function, but it returns a new proof that something else can use. And the same thing with j. Pass in the proof of j to set j equal to 2 and get a new proof p of j1. Now, here I have swap that takes ij and a size of parameter, but I have to give it the new proof p of i1 and p of j, oh, that should be p of j1, sorry, typo. And it hands back it's a void function, it hands back a proof of p of i2 and p of j2, right? Because we need those to free the resources. Here I'm freeing I, passing in that proof of p of i2, and freeing j, passing in that proof of p of j2. If I didn't have those frees, that would be a type error. Because any unconsumed proof left lying around after the program is complete is a type error because according to ATS, that's a leaking resource of some sort somewhere. You have to clean up all your proofs. Like, you have to clean your plate because there's starving type systems that don't have proofs or something. So the same thing. I don't free that, I get a type error. I pass in something, size of something other than int, I get a type error. I don't pointer set, I get a type error. Basically, everything that can go wrong with swap is a type error, except for if I went swap ji instead of ij, that's actually not a type error. There's no amount of like typing that would actually make that work because of type blindness. So I don't care how whiz-bang your type system is, please test your code because there's something that it doesn't see. But here's the original code. Here's all of the code that's dedicated just to proof threading, right? And there's some Haskeller in the back going type level state monad or whatever, you know? But ATS is like, LOL, how about implicit proofs and syntactic sugar? Because that solves everything. So here's an idiomatic swap in ATS that bang P1 syntax means there's a pointer called P1, bang means dereference this, but first look around in scope for a proof that might work. And use it. There's absolutely no bug vectors here whatsoever. but the story is that like implicit syntactic sugars solve all UX problems. So remember that if you're designing a language. Let's take a huge step back at this point. Anybody overwhelmed? Because that was a crap ton of syntax, right? Breathe. There's more. It's coming. And I haven't even shown you the type errors yet. And I'm not going to. Because they look like those like taunting code messages that serial killers send to cops. That's it's rough. But at the same time, I still think that you should look at ATS, not for, hey, adopt this now, but this idea of passing proofs around is so powerful, I think. I think it's the future of systems programming. Like Rust has this idea of linear logic, right? But all of the linear logic stuff, the cool stuff, is back behind sort of the lifetime analysis mechanism and sort of the borrow checker and stuff like that. I want first-class access to those proofs. I don't want them back behind something for the sake of some error message, because I think I can have much better designs, much more flexible designs, if I have access to that stuff. And I think that if you're designing a systems programming language, which one of you probably is, right? Please do this. Please take from this. Okay. Like I said, ATS has first-class support for recursion. And in fact, it encourages recursion unlike other systems programming languages. So other systems programming languages don't like recursion because it stops over the C stack. This is also true. ATS encourages it because it allows the type checker to prove things by induction. So here's a factorial function in ATS. There's a lot of gook there. So let's look at the essential complexity here. There's a top-level function, factorial. There's an inner function loop. You kick off loop with 1.0 and I. And as you've all probably surmised, it's an accumulator that ends up accumulating inside in that first argument. We parameterized factorial with an integer. And it outputs a double. We modify that integer such that it always has to be greater than or equal to 1. You can't call factorial 0. We propagate that constraint to the inner loop. And the inner loop takes an accumulator, which is a double, and an I, which is an int parameterized on that constraint, saying that it has to be greater than or equal to 1. And this funny-looking thing, hello more syntax, called a termination metric. A termination metric, the thing inside that angle bracket, is a number or an arithmetic expression that you have to show the type checker is strictly decreasing on every recursive call. This is how the type checker knows that this recursion will eventually terminate. A lot of C coding standards don't want you to use recursion, especially for critical code, because you can't prove that the thing will terminate. ATS gives you a way out of that. So I'm pattern matching on I. Don't worry about why it's case minus. We'll get to that in a second. Or maybe we won't. I don't know. If it's 1, just hand back the accumulator. If it's not 1, when it's greater than 1, make the recursive call. Multiply the accumulator by I and decrement I. The most interesting thing about this example is not that it works, is what happens if you leave stuff out. If I leave out that when I is greater than 1, that's a type error, because it's going to say you have this constraint saying that I has to always be greater than or equal to 1. More interestingly, if I do anything other than I minus 1, if I do I minus 2, if I do I minus 3, the solver is smart enough to say that you might skip right past 1, and I can never ever show that this is going to be greater than or equal to 1. If I do I plus 1, that'll piss off the termination metric, right? Because now the thing is not strictly decreasing. So ATS uses recursion to prove useful things about your programs, when, in my opinion, most other systems programming languages stay away from recursion for good reasons. It messes up the ABI and all this stuff. But I think there's some good reasons to use it. Okay. So the next big thing is view types. So view types are this thing that connects linear resources to algebraic data types. Remember, I told you ATS was an ML. So we want to be able to use all of this like functional programming abstraction goodness to control these linear resources. And that's what view types do for us. So to see what a view type is, here's the problem. This is the swap definition that we saw earlier. Taking away some of the duplication, here's what we have. We have a type of unknown size, we have an address greater than null, we have a pointer to that address, and some proof that there's something of type A at that address. This comes up a lot, right? A pointer to something that you want to know is not null that has something inside of it, right? If we're going to work with ATS at a higher level, we need to somehow package all these things up. And the way to do that is with this thing called a sort def and a view type def. I didn't name these things. So a sort def basically takes that constraint and gives it a name. I'm calling it in fact, I'm not calling it AGZ. It's called AGZ because that stands for address greater than 0. Okay. And a view type definition that takes that proof and that pointer and packages those up together with a constraint on it that the address can't be null. And we call that safe pointer and parameterize that with something. Okay. Now, okay, sorry. So this type signature cleans up to that with those view type definitions. And now we have a basic building block. And we can create algebras on linear resources. This is a cool thing to have. So here is the algebraic data type of a list of view types, a list of linear resources. Cleaning some of this stuff up, this should look relatively familiar. So instead of data type, I have data view type, but I still have two constructors there, a nil constructor and a cons constructor, and the name of the data type, which is list underscore VT, which is going to be parameterized on a couple of things. One of which is a view t at YPE. I did not name this. It means a view type of unknown size and an int. The nil constructor takes that thing we passed in and 0. This is a type level number, 0. Okay? The cons constructor takes that a and an n, which is an integer, and hands back the a and recurses on that list view type and decrements a. And you can also provide constraints on that. So basically, if you have a linear list of like 1, 2, 3, right? It will be linear 1, it'll be list VT cons 1, list VT cons 2, list VT cons 1, list VT cons 0 at the type level. That's what it would look like because it's decrementing that at the type level. So here we have how you construct a linear list. List VT cons 1, list VT cons 2, list VT cons nil. None of this stuff is really interesting. What's interesting is the type signature, which is usually inferred. This ATS can actually infer. It can infer precious little, but it can infer that. Right? So it's saying it's a list view type of type int, and there's two things inside of it. Cool. So what we're going to do is use that to make a factorial that preserves the results in a list. So basically, if I'm calling factorial 10, I don't just want factorial 10. I want 10 times 9, 10 times 9 times 8, 10 times 9 times 8 times 7, all the way down. So the last thing in my list is going to be factorial 10. I want to preserve all that stuff. And here's the function that does that. So again, removing some of that complexity. The new concept we have here is this new keyword, var. Var does not mean what var means in every other language in the universe. Var means a stack allocated variable that decompiles to a stack allocated variable in C. That's all var means. It is mutable, but it doesn't mean mutable. It means stack allocated. And here what we're doing is saying we're stack allocating a pointer that is uninitialized. And then we have that function loop that we kick off, but we're returning that var down at the end. So we have a factorial that's parameterized on some integer. that's modified, so it always has to be greater than or equal to 2 this time, not greater than or equal to 1. I'll get to that in a second. It returns a list view type of a bunch of doubles where the length of the list is n minus 1. Why? I'll get to that in a second. Because we're initializing it with the product of the first and second thing. So if it was factorial 10, the loop is going to be initialized with 10 times 9. So like that G0, 1, 2, 2f is the method name for coerce an integer to a float. I'm sorry. And so we kick off the loop with that initial thing, and then we go I minus 2 because we've already accounted for the first two things, and then we pass in a reference to that stack pointer. Now, this is the inner loop. This is just the type signature. So let's step through this. So it takes in a next argument, which is what is the current index of the factorial that I'm on right now, which is parameterized by n1. And n1 is an integer that's greater than or equal to 0, but less than or equal to n minus 2. Why n minus 2? Because we kicked off the loop with I minus 2, right? Okay, cool. So n1 is also the termination metric. You have to prove that that number is going down on each recursive call. It's also parameterized on that seed, which is a double. And this is cute. It's parameterized on this result type. And the ampersand means a reference to. The question mark means uninitialized. So this means a reference to a pointer that's possibly uninitialized. That's what those 1, 2, 5 characters mean. And it transforms that into a proof. That's what the 2 arrow signs mean. It keeps getting better, don't worry. It doesn't. Into a proof that it is a list of view types of type double that is of length n1 plus 1. Why n1 plus 1? Because n1 goes to n minus 2, and we want n minus 1 because there's always one less thing inside of that list than you pass in. And yes, this is super confusing. Okay, I know this is super confusing, and I left it super confusing for a reason, because I can hash all this out at the type level. These are exactly the kinds of things that go wrong. Imagine all the tests that you don't have to write, right? These off by 1 things happen all the time, including in languages with really strong type systems as we think of them. Like Haskell, will have off by 1 type errors. All of these things will have off by 1 type errors. Rust can have an off by 1 type error. With refinement types, you cut the number of bugs that you put into your production code by a lot, just by having that check at the type level, because the type system will not let me go forward unless I can prove that all those relationships between those numbers are sound. Cool. So here's the inner body of the loop, which is similarly complicated. And here are the arguments for reference. So we're pattern matching on next. In the case of 0, I'm just setting the result, the stack allocated pointer we passed in to the seed and nil. So if all we did was passed in 2, it would just multiply 2 times 1 and hand that back in a list. For the next part, I'm going to take a step back and propose a puzzle. Solve this puzzle in a strict functional programming language. Pick one, doesn't matter. Fold over a list and give me a copy of it. That's all you got to do. Make it as efficient as a while or for loop with an initial null that has in-place mutation. But here's the kicker. These are your constraints. You only get 1 pass, no reversing at the end. You iterate through this. You can't iterate through this list and start accumulating things and then reverse it and hand it back to me. That's more than 1 pass. And it's not more efficient than a while or for loop. No macros. No building up a bunch of terms and then evaluating that in the end. That's cheating. No continuations. No building up continuations and evaluating that at the end, which is kind of the same as the macros, but I feel I have to specify that for this crowd. No peepholing. No function called copy list where the body of the function is just a while loop. That's cheating. No weird optimization pragmas. Yes, I'm aware that there's like some super smart compilers out there that you can give like this magical incantation to that can make all this go away. That's cheating. I think that this problem is probably impossible. Pick your favorite strict functional programming language and look at the implementation of map in it and see how it does it. Milton, the standard ML that is all about performance, reverses. So if you look at the source code for Milton's list map, it applies a function to everything in the list and then reverses that list. So it's taking 2 passes. OCaml, peepholes. So OCaml has this like mutable accumulator that it keeps tacking on to the end of. That's the same as a while loop. That's cheating. Rust I think uses macros, possibly, or peepholes, one of the two. Or it just writes it in LLVM, as far I don't know, right? But until recently, I considered all of these things elegant hacks. And now I'm just dissatisfied. And by the way, people keep saying that like learning programming languages makes you a better programmer. It really doesn't. It makes you a better programmer up to a point. Then it makes you bitter and dissatisfied. Because you will never be able to port those ideas to your day job. Even if you could get past the technical hurdle of your programming language not supporting those constructs, you will never get there, and you will be bitter and unhappy. So you should all just leave right now. Like, but if you're going to stick around, ATS supports this thing called tail allocation. Tail allocation was an idea that was floated for ML in 1998, and I learned that because I was researching, when I was researching ATS, I came across this idea. And it's 20 years, and nobody else has adopted this. Please adopt this. Okay, so what is tail allocation? Tail allocation is a way of punching a hole in a data structure. Punching a hole that will be filled in later on. In a way, you can think of it as a principled null pointer, but it's not quite that. Okay. So, let's get back to our loop. Cut out some of this code, and look at that let block. So what we're doing is setting res, which is the return pointer, equal to some list, with the seed as the first thing, and this uninitialized hole as the second thing. This underscore on the right-hand side of an equal to sign means I'm going to be filling this in later. Now we have to actually pattern match on res to get a hold of that hole because ATS doesn't give us a way of like having named holes in one pass, unfortunately. So that underscore is that hole. And then we calculate the next, seed because we have to use that cheesy G012F function, which courses from an integer to a float. Again, I apologize. And then we call loop and pass in that hole. And that's the hole to be filled.
Is that plus a typo?
No, nothing's a typo. He asked if that plus was a typo. Nothing's a typo, but I'm just not going to tell you what it means. Because that's a rabbit hole. So what it really comes down to is this sort of circular reference thing. Res creates a hole, the hole goes back into loop. On the next iteration of loop, res creates another hole, the hole goes back into the loop, and so on and so forth, until the until the zero case on top, where it fills it in with the final seed and a nil. And that's how you get, in ATS, folding over a list with this exact same performance profile as C. And in fact, you can even see how that, you can even envision how that would decompile into C. And that's a really powerful thing to have. These kinds of things are really powerful things to have because functional programming already has a reputation for being slow. Like, we have words like maintainable and stuff like that, but once you say maintainable, most people have just sort of already gone. Like, C programmers don't care about that. Okay. So that was my final example. So here's some takeaways. ATS is rough. There's no two ways about it. This was just a taste. This is the tip of the iceberg. But it contains, I think, like very promising glimpses. This would be, if a bunch of programming languages took these ideas and ran with them, I think we would have a great systems programming future. Linear logic is a great idea. I want first-class access to that. Don't baby me away from linear logic. I want those little proof things that I can manipulate. Refinement types, great idea. Other languages are coming around to it. Liquid Haskell is one of them. The idea of having a smart type checker and a dumb compiler is great. So that's what ATS is. ATS is a front end to C that decompiles into C code that you would have written in the first place, or semantically equivalent to that. And this idea of having a front end on a language that's already widely used, I think is a really good idea. Like, think TypeScript, but just keep going. Like, run with that for like the next 20 years and see what happens. Forget about like usability. Just run with it, you know? And there's a whole bunch of stuff that I haven't even talked about yet. ATS is a whole proof level language. It supports proof by induction, pattern matching and everything. So for instance, in ATS, there's this concept of an array. Like, it's the same as a C array. Basically, you have a bank of proofs that like these pointers point to these locations. And I can write a type level function that looks rather like ML that breaks up that bank of proofs into two separate proofs, saying that here's a proof going from index 1 to 5, and here's a proof going from index 6 to 10. So the slicing that other languages provide as a built-in is, you can do it at the proof level here in ATS because you have that kind of flexibility. So in any case, that's my talk. Here's the repo. There's way more resources. I just didn't have time to add those. I will. And thank you for your time, and I'll take any questions.